Alright, hello everyone. Welcome back to the channel. Today we're going to be talking about some good old-fashioned quantum mechanics. Without further ado, let's dive right into it. So the first thing that is absolutely essential to understanding quantum mechanics is that of particle-wave duality. So let's talk a bit more about light as a particle. In the early 1900s, Albert Einstein discovered that light mainly behaves like a wave, but it's also considered to consist of tiny packages of energy called photons. So he did this really cool experiment called the photoelectric effect, which basically demonstrated that light can exhibit particle-like behavior, even though up until now, most of the experiments that were going on showed that most of the properties of light reflected that of a wave rather than a particle. And so this was a very instrumental experiment in understanding wave-particle duality and just the furthering of quantum mechanics as a whole. So light is a wave. Um, but there were also a couple of experiments that proved that light is a wave as well. One of those is the famous double slit experiment, which basically consisted of photons being shot through these two separate slits in a hole onto a just like a background. Um, and so what was expected was there would only be like these two ranges of um, these two bands of light after the photons would be separated by the slits. In reality, scientists observed that there was actually more like a spectrum of these wavelengths that were showing up on the backboard. So this could only really be explained by the fact that light is a wave, because light is a wave, many different peaks and many different crests of the wave would pass through the slits and then exhibit their own diffraction patterns and then show up on the backboard as a result. So this is another very important experiment that really showcased that light was a wave as well as a particle. So this led to what we think of these days as light-particle duality, which is basically just the idea that light behaves more as two things, as with a with a wave and both as a particle. So something called an interference pattern is seen through a um, what's it called? Is seen through a double slit experiment. So there's the link on YouTube. You guys can feel free to go and look at that whenever you want. Okay, let's think of the Heisenberg uncertainty principle. This is another very important part of quantum mechanics because it is roughly everywhere. You can't really go too far in quantum mechanics without bumping into the Heisenberg uncertainty principle. So the Heisenberg uncertainty principle considers the act of measuring an object state changes in object state. So basically, if you're studying an electron, you can't really know the exact position um, and the discrete velocity of the electron at the same time. Because inherently, when you're observing the electron, you are changing the electron's state. So let's look at this one example of Stephen Curry. Every time you're looking at the basketball between Stephen Curry's hands, you are inherently changing its state because you are observing it. So let's talk about the wave function. And this is very, very essential to any and all quantum mechanics. It's basically like Isaac Newton's F equals ma in like just the quantum mechanics sense, which is extremely important because it tells you all sorts of different things and is extremely, extremely helpful. Um, so yeah, the wave function uh, basically says that the value of the wave function at a certain point is related to the probability of a particle being at that point. So this is where things like electron orbitals come from. So looking back to, again, the Heisenberg uncertainty principle, we see that we can't discretely measure both the exact position and the exact velocity of the electron at any given time. But what we can do is we can come up with probability distributions of where the electron might be around the nucleus. And so that's led to more of an updated sort of considerance of electron clouds rather than discrete electron shells. But energy levels for electrons are still determined by wave functions because as you increase in energy levels, the number of probability distributions per energy level increases, which is also determined by the uncertainty principle and the wave function. So yeah, that's that. This is just a very brief introduction to quantum mechanics. My next video is going to be more of a deep dive into quantum mechanics and how it's more useful in astronomy and astrophysics. But thank you all again. It's been great, and I'll see you in the next video. Thank you.